Alright, so today we're going to talk about the definition of a limit. So what we want the limit to describe, it's the behavior of a function when x gets really close to a point but not at the point. So if we studied a simple function, we see that this function is undefined. If x is 2, you would be dividing by 0. But if we were to factor this, we see that we can make a cancellation of x minus 2 provided that x is not 2. 0 over 0 does not cancel out to 1. So and if you were to graph this function, what would happen, what you would get, you would get the line y equals x plus 2 for all values of x except for 2. But when x is really close to 2, this x plus 2 term would be really close to 4. And what we see is that we can make this function as close to 4 as we want by simply making x really close to 2. So this is the idea of a limit. So now we need to start to formalize it. So what does it mean for the limit as x approaches c of a function to equal to a number L? Alright, so what I'm going to do is I'm going to start with a preliminary definition in plain English, and then we are going to abstract it into math. So, what this means is that we can make f of x as close to L as we want by making x close to but not equal to c. So we can make, in this case, our function we can make this function as close to 4 as we want simply by making x really close to 2. Okay. The problem with this definition in English is this phrase, close to. It really has no mathematical meaning. If you're an astrophysicist, you may say two stars are close to each other if they're light years apart. If you're a particle physicist, close to might be nanometers or microns apart. So what we have to do is we have to quantify how close is f of x to L and how close is x to c. So, how close is f of x to L? Well, the answer, we use the Greek letter epsilon. Okay. How close is x to c? And for this distance, we use the Greek letter delta. Okay. So, going back to our diagram, here would be c, here would be L. So if we want our function to be close to L, how close? Epsilon close. That means that we can be epsilon above L or epsilon below L. So that means our function could be between L plus an epsilon and L minus epsilon. So we're going to keep our function epsilon close to L by keeping x close to c. And how close is x to c? The answer is delta close. So this distance here would be delta. Which means if this is c, move delta to the right, you would get c plus delta. And move delta to the left, you would get c minus delta. Okay. So what I'm going to do, based on this diagram, I'm going to start creating a string of inequalities and if-then statements. The very first if-then statement, based on the diagram, says if x is between c minus delta and c plus delta, or between here and here, then the function f of x is in between L minus epsilon and L plus epsilon. And we see that from the diagram. And this is very similar to the if-then statement in the definition, but what mathematicians have done is they have tried to compact this. So what they do from this first inequality is they subtract off a c. So then it becomes if negative delta less than x minus c less than delta, then, and from the second inequality, they subtract off L. Negative epsilon less than f of x minus L less than epsilon. Okay. And if this, then they compact it even more by incorporating absolute values. Remember from pre-cal that if you ever have the absolute value of a function less than a number, this is logically equivalent to saying that the function is between the positive and the negative of that number. And that's what we see. We see negative number, function, positive of the same number. We see that twice, the negative of some number, a function, and the positive. And we see that over here. So what we do is we package these inequalities up in absolute values. So this becomes if absolute value x minus c is less than delta, then absolute f of x minus L is less than epsilon. Okay. And this is almost identical to the statement you see in the definition. The only thing that we really haven't incorporated is this last sentence. We want x to be close to c, but not equal to c. So how do we prevent x from ever equaling to c? Well, we know the absolute value of something will never be negative. So the only two options for absolute value of x minus c is this is either positive or this is 0. And the only way for it to be 0 is if x is equal to c, which we do not want. So we prevent x from equaling to c by forcing this to be positive. So we get alright. And this is the exact if-then statement we see in the definition. So let us now formalize the definition. And I do believe you will have to state the definition on a test or quiz, so make sure you memorize it. So, get it out of English, get it back into math. So, alright, so we can make f of x as close to L as we want. So, for any distance epsilon, this should work. And a distance must be positive. So, the first statement in the definition, for every epsilon greater than 0, for any positive distance on the y-axis, there will be a distance around c. So, and again, a distance is positive. There will be, or there exists, a delta greater than 0, such that, and then we have this if-then statement. If then okay, so that is the formal definition of a limit.